I don't know, but it's not due this Friday. Studying for the exam, that's a real quick skeleton there, because I've been getting questions about this. So, based off of past student experiences, do the online homework and do it well in advance of the class. That makes life more difficult for you because you're working on questions that you've never seen before. Okay? It's a little bit easier to do in second semester because you have a fundamental understanding of everything. A lot harder to do in first semester. It still is the best way to get through it. Get the online homework done early. So let's say the exam is next Wednesday. It's not, so don't immediately freak out at that. Let's say it was next Wednesday. Your online homework should be done today. That's how in advance we're talking about, all of it. Okay? We still have content to cover. Okay? You should have already worked through the reading of the book and trying to get those questions solved. Okay? At least currently, there is no penalty for attempts, except for Chapter 1. I apologize. I can't change it now. Okay? But every other chapter, there's no penalty for attempts. So you could go through and try them an indefinite amount of time. Stop doing that, because all that's doing is building frustration. You get 3 attempts before you send me an email. Okay? It's not that difficult, just 3 attempts. I don't know what the hell's going on, send me an email. Okay? Let me know the chapter and the homework or the question number, and I can go and look at it and find it. Okay? And I can see if it's a content issue or if it's a programming issue. Some programming issues have popped up already. Okay? I don't know why they're there. SmartWork people promised me that there were going to be no issues. Okay? So they're going to get a follow-up email of me screaming at them. Okay? Yes. So homework, theoretically, so again, same pretense or context. The exam is next Wednesday. Since you just walked in, it's not next Wednesday. Just for giggles, we're saying it's next Wednesday. Online homework is done tonight. What do you do for the rest of the week? There's the practice exam. Take that practice exam. It should be done by this Friday. Okay? Why? Because this Friday you can send me all of your answers. I can go through it and be like, this is why you got this question wrong. Or I have no idea why you're getting this question wrong. You should probably go back and reference your notes to figure it out. Okay? If you give me permission to, I will then post your answers so that everybody else can see them. Okay? And my comments to them. I will not say an answer is correct. I will just point out when you're wrong. Okay? You can then spend the weekend reviewing what you got wrong and preparing for the exam the following Wednesday. Does that make sense? That's the ideal prep behind the course, okay? At least as far as turning in work goes. Okay? Yes, that means you have to be well out in front of it. As you may or may not have seen in the announcement I posted, we have a lot of content to try and cram in. We're now week 3, and we officially have talked about all stuff that you should have already seen and roughly mastered in first semester general chemistry. Okay? I'm not saying that's your fault that you haven't mastered it yet. Okay? That's just the way it is. But that's where we are with our content. Questions about that? Questions about anything else? Okay, then we're moving on. So, drawing our organic molecules, because I had the nice pictures. We'll look at the nice pictures. If we were told to draw that formula, there's a bunch of different ways we could have drawn out our structure and it wouldn't have helped out. Okay? Or we could have been wrong. If we provide a structural formula, that provides a little bit more context, allowing us to get to what that compound looks like. But even then, that structural formula or condensed formula doesn't give us all of the information. We lose a lot of information by drawing it like that. So we could draw it out as the full-on Lewis structure. Okay? A lot messier, but it gives us a better context of how that molecule reacts. Okay? A good way to describe this, whoops, don't do that. There we go. Is doing this. What did I just write? Which one gives us a little bit more context of what's happening within that structure? Okay? The stick figure gives us more information. Why would we sacrifice that information? typewriters, computers, it's easier to write it out in that linear format. Okay, that is changing. Structures are going to start to become the norm. Okay, whenever we're working with stuff in this class, we want to be looking at structures. Okay, what sucks is what do you get tested on?
Names.
How do you move from this structural formula, because the test is written on a computer, to a structural formula to be able to interpret and see how it's going to react, to then look at your answer choices, which are back in the structural formula. You're expected to do a bunch of flopping back and forth between these interpretations. Okay? That comes with practice. Okay? Or in my case, it's still not there. The only practice I've got to be able to answer questions is that I can draw very, very fast. Okay? So that I don't do those inner conversions in my head. That is what I would recommend you do. Draw them out. Okay? Lewis structure doesn't show everything. So we could fold Vesper shape into it, and we get wedges and dashes and bond angles and lots more information, but you would probably agree that that is confusing. Okay? So we could go to line angle Vesper. Say, well, we're in an organic chemistry class. There's no point in drawing out all the carbons because they're going to be everywhere, so I'm going to imply the carbons. The carbons are just going to become points at the end of any line. And if I want something other than carbon, well, I'll draw my normal line and just draw a different atom there. There's a hydrogen at the end of that line. So all of these are roughly, or are equivalent. You'll still notice there's a lot of hydrogens. So you go, why do I need to draw all those hydrogens? Because they're always going to be in there to satisfy the octet for our carbons. So I'm just going to ignore hydrogens outright. And we end up with line angle abbreviated. I don't even know if that's the right term, but that's what we end up with. So when we're thinking organic chemistry, this is our home. We sit in this line angle abbreviated. Okay? And we're required to know each of those simplifications behind each of those steps. And not even know that they exist, but recognize that if I'm going to do something with this structure, I may have to convert it into a Vesper structure to be able to come up with that interpretation. Kind of make sense? Okay. If we put this all into kind of words, our first simplification, we've got a few elements that we're primarily focused on. That's probably true for the entirety of this semester, just those elements. That's a lie, we'll see aluminum. But that's like boron. And we'll see probably sulfur. Okay? The next part is our simplified shapes and hybridizations. We don't have to deal with octahedral or trigonal bipyramidal. We just have to deal with tetrahedral and lower. Okay? And then we move into our abbreviated drawings. Every point is defined as a carbon. Okay? If I want it to be something else, I must specify that something else. Okay? Hydrogens will be implied, but they will only be implied to carbon. Okay? And they're there to satisfy the octet. Which means if I draw a structure like this, how many carbons are present? 4. 0.1, 0.2, 0.3, 0.4. How many hydrogens?
10.
3, 6, 9, 10. How many hydrogens?
9.
9. We have to very quick, subtle changes to our drawing drastically change this out. How do I know I lose a hydrogen? For a carbon to be missing its octet there, to be positively charged, it can't be bonded to a hydrogen. Otherwise, it would have its octet, and it wouldn't be charged. Does that make sense? Okay. Which gets us to the next rule. We will never imply a charge. If I'm going to refer to that as a carbocation, I have to show it there. Because if I don't put the positive charge, I have an extra atom. That makes a really big deal. Okay? So you will always, always, always specify charges. Okay? And the reason we have to do that is because we're trying to figure out our implied hydrogens, which also ties into, unfortunately, our implied non-bonding pairs of electrons. How many hydrogens now in that structure?
9.
It's still 9. Okay? I don't imply the formal charge, so it's specified, but I have implied the lone pair that makes that negatively charged. Okay? Implying non-bonding pairs of electrons is a really bad idea for first semester. I will try my best to always show them, but it takes time and effort to make sure they're shown in there. I would highly encourage you, particularly at this stage in the semester, to always draw them in. Okay? Or call me out for not drawing them. That's fine. Okay? But you will find eventually they start to get implied. Okay? And you're responsible for knowing they're there, just like the hydrogens. If we move to the next one, nitrogen, oxygen, halogens, those are the ones that we really see non-bonding electrons floating in there to satisfy octets. And those are very often implied. Kind of make sense? Okay. So those are our kind of rules that base the rest of drawing structures. Okay. Yes, there's other things that kind of float in there, but for the most part, that covers our bases. Okay. Ideally, by this point, you've got this roughly memorized. You know that when you see a neutral nitrogen, you know it has 3 bonds and a lone pair of electrons. You know that when I'm talking about a negatively charged halogen, it has 4 non-bonding pairs of electrons and no bonds. Okay? You may not be there yet. You may not even be there by the end of the semester. You need to be working towards that and recognizing those patterns very, very quickly, because we have to use those. Does that make sense? Okay. So, kind of chapter 2. What dictates all of our functionality? Okay. Our functional groups are ultimately taking a look at how we connect atoms with each other and how those atoms perceive or see each other. When I bond a carbon next to an oxygen, what happens to the electrons between them? Oxygen having more electrons on its own, I don't quite accept as an answer.
The electron density shifts towards the oxygen.
So let's reference just
bond.
the electrons in that bond
In that bond, the electron density in that bond shifts.
are now shifting towards the oxygen. Why? Electronegativity. So this is why we talked about the trends in electronegativity within our periodic table. The more electronegative the element is, the more likely it steals those bonding electrons. That starts to generate charge. Well, why is that important? Is charge stable? No. And for those of you that question that, number one, do not do this example, but it should be enough to jog your memory of how unstable charge is. Take a metal fork and shove it in the electrical outlet. Charge is not stable. Do not do that. Good? It's a safety thing. I gotta make sure we're covered. Okay? Don't do that. But that's your example of charge. Charge is not a stable thing. Okay? So what we're looking at is then how does that shift outwards? Well, if I have a negatively charged oxygen, or an oxygen that's starting to become negatively charged, what is it going to want to do to that charge?
Get rid of it.
Neutralize it. So it's going to have to do that by sharing some of those electrons with,
Probably a hydrogen or a carbon.
I would argue we don't even need to get that specific.
Another atom.
What other atom?
And
Not any, because a negatively charged oxygen will probably not interact with fluorine. Why not? Fluorine, being the most electronegative element on the periodic table, is likely carrying a negative charge. If I put a negative near a negative, they repel away from each other. What do we put near that oxygen to stabilize that negative?
something positive.
Something positive. How do we know that something is positive?
It'll have low electronegativity.
Because it has a low electronegativity. Could work. Okay. Could I put, would I expect a strong interaction between a negatively charged oxygen and say this hydrogen. Hydrogen has a low electronegativity. Would I expect a strong interaction there?
No,
Why not?
because there isn't a pole, there isn't a strong dipole on that.
What does the negative need to stabilize?
A positive.
A positive. Just because we have a low electronegativity atom does not make it positive. What is this hydrogen bound to? A carbon, which is low in electronegativity, which means is that hydrogen very positive? No. How about now?
Now it is.
Okay. Now we can see that difference. So we can use electronegativity to help us predict reactivity. Okay? And we can use that to say that HCl is,
Polar.
keep going,
Cl negative, H positive.
too far. Come on, Gen Chem. HCl is hydrochloric acid. We have an acid. What? That's all you wanted? Yes. Okay. We came up with a name to classify it for things that functioned like this. So we could then call them all acids, or we could call them all bases. That was the birth of functional groups. Okay. When we move to organic chemistry, we now have to take all of those elements that we've been playing with and start to put them near each other and say, well, what happens? Okay. If I put a hydrogen, this should say single, next to a carbon, I'm just generating an alkyl type functional group. Okay. Without more specifics, I don't know if that's an alkene, an alkene, an alkyne, or an alkane. Okay. So it's just an alkyl. Nitrogen next to hydrogen, well, now it's an amine. Oxygen next to hydrogen, it's a hydroxy. I don't like referencing it as a hydroxy, but we'll deal with that bridge later. Okay? So all we're saying is that when we put those atoms near each other, the difference in electronegativity causes a slight change in that reactivity. That change now allows us to establish a functional group name. What happens if I take multiple functional groups and I put them near each other? So let's take that hydroxy, and I'm going to put it near an alkyl. What do I have now? So we've got a little bit of nomenclature creeping in there from some people that have that experience. A single carbon. One carbon is known as a methyl. There we go. So it is a methyl. What is the functional group? Spring break. It's an alcohol. Okay, don't be drinking this during spring break, by the way. I should have picked a better one. Okay, we have an alcohol. We changed the term of hydroxy, okay, and our alkyl, and we changed it now to call it an alcohol. Okay, because we've combined those functional groups. All of these kind of names that are listed through here aren't full functional groups because they aren't a full structure. Once we put the full structure around it, we can build our functional group. Okay? And why do we have those different names?
So we can understand the differences between them and the product.
You can understand what they're made of. Complicated.
Okay, so we had the option of this one. So if we just draw it like that, our functional group is an alcohol. What happens if I combine or put near the hydroxy, I put carbonyl? Doesn't that still have the alcohol root? Shouldn't that be called an alcohol? No, why not? This extra piece messes with this extra piece, and we get a carboxylic acid. I don't want to write carboxylic, but it should be there. Okay? Why is that an important distinction to note? Does an acid act differently than an alcohol? Yeah. Okay? So the whole point of knowing our functional groups is it allows us to predict something about their reactivity and how they might interact with the outside world. Okay? So there are tons of functional groups that you could be looking at. Okay? What I would argue is this slide summarizes the majority of what you would need for this semester. Okay? Within this, not only am I providing a Lewis structure, arguably kind of the nasty looking Vesper style, okay, but I'm also providing a shorthand formula in case it was typed out. Okay? A favorite one to show up on tests would be in the upper right-hand corner. What you looking at? Sorry, that was really bad. Aldehydes tend to get abbreviated CHO, okay, which tends to confuse people when how it's put together or built in a formula. Okay, but that tends to be how it's set up. Ketones do the same thing. We have the same functional group or the same bond type, a carbon-oxygen double bond, but located in the middle of the structure. You might see parentheses on it. Why do you need parentheses? What if you didn't put parentheses on it?
I would assume that there's hydrogens.
Starts to become
Oh,
an ether. Why is the parenthesis there? What is bound to that oxygen? Just the carbon in front of it. Okay? That's why we have the parentheses. If we don't have the parentheses, and of course I use the other abbreviation for ethers, awesome. The oxygen is now being assumed to bond to both carbons. Kind of make sense? So very subtle changes in how we represent these. Okay? So you should memorize all of these functional groups. Okay? You don't have to be able to name all of them, at least yet. Some people get a bit daunted by this list, and to that I could say open up the textbook to their list of functional groups and memorize that list instead. What you will find is their list is longer. Okay? These are the biggest, easiest ones to memorize, to deal with. The next part that I could also say to this is, what is the name of P? Touche, yes. Let's try it, everyone. What is the name of Cu? Copper. Why do you know that? You had to memorize it for general chemistry, because this was the language of general chemistry. This is the language of organic chemistry. You've got a new language, new words. You've got to memorize them. Okay? So, reaction versus interaction. I kind of want to whip through this a little bit. What is shown on the board right now? Okay, and we can simplify it, make things easier.
Salt.
I'll accept that. Salt. What else is up there? A bond. We have a bond between sodium and chlorine. What do I have now?
Salt and the bond between sodium and chlorine.
It's the same thing. Little blue thing. Is that a good thing to draw there?
Yes. No. No, it is not.
Okay. So we've got a volunteer for no, so the rest of you get to come up with why.
Because they wouldn't attract each other.
What do you mean they wouldn't attract each other?
Well, so they're both negatively charged.
How do I know they're negatively charged? I don't accept chlorine being a nonmetal.
Chlorine is much more electronegative.
Chlorine is more electronegative than sodium, meaning chlorine steals those electrons and becomes negative, the sodium becomes positive. Same thing's going to happen on the other side. I would have a negative to a negative. Is that a good interaction to show? No, that's compiling more charge into the same area. That's more dangerous. We don't stick the fork in the transformer coming from our power lines outside, much less frequently than we would in the electrical outlet. Okay? A lot worse. Okay? So what would be a better way to draw that without showing all the other ones? Okay? Cool. I like that. We have that negative to positive. Have I shown something different now than we said we had to begin with? Those of you that were wondering what we said to have begin with, that's a good question. What did we say we had to begin with? The Cl to Cl, or the sodium to Cl bond. We have a bond. Do we have something different now? Yes? Why are you saying yes?
Because it's not directly bonded to each other, it's an interaction.
How do you know it's not directly bonded?
Because they've already been neutralized. There's no need to.
It's not a straight line, but you drew with those dashes.
That's not a straight line. Okay? That's it. It's not a straight line, so it's not a bond. Okay? And yes, that seems silly. It's those silly observations that drive what we're working with. You have to understand the meaning behind those symbols. So what is that silly new thing that's not a bond? It's a force. Okay, we have a force here. Describe a force to me, if you will. I like it. Attraction. Your timing was phenomenal on that. It's an attraction. Describe a force to me.
Something weaker than a bond.
Both of these are attractions. There is no difference. They are attractions. All that's happened is we have arbitrarily decided that at one end of that attraction spectrum, it's strong enough that we're going to call it a bond. At the other end of that spectrum, it's not strong enough to call a bond. Okay? The difference between those, you may have been told, is this sharp, crisp line. It's not. Right? It is a massive gray area in between. We're looking at transitioning as we move from a bond to a force. And for those of you that say, well, how would we know it's such a gray area? What is the sodium bonded to? Chlorine. What is this chlorine bonded to? What is different about that interaction?
Nothing.
That I drew a dashed line instead of a solid line. That's a pretty arbitrary nonsense answer, which is why nobody said that to begin with. Okay? But that's what's happening. We've got a very subtle difference, particularly when it comes to the ionic bonds. Okay? They could be a bond or they could be a force, depending on which end of the spectrum we really feel like staggering and applying that definition. So we do have to recognize that these are interrelated things with different meanings. Because when will forces be used? Intermolecularly, which is a fancy way of saying between molecules. When is a bond used? Within a molecule. So you guys went fancy and then decided not fancy. What's the fancy way? Intramolecular. Okay? That's what differentiates these. Okay? And the difference between those is very, very subtle depending on where you're looking at within that spectrum.
You get into crystallized stuff, and then it's kind of.
Yep, I didn't even bring in crystal lattices because that opens up a whole other can that I don't want to deal with.
In ionics, it's kind of iffy whether it's intra or inter.
Yeah. Because of where you arbitrarily drop that line. Yeah. Okay? So, intra versus inter. We talked about ionic, polar covalent, and covalent. And we gave up definitions for each of those, right? Okay. Not only did we give definitions, I also said that what you should do is not memorize the definitions, because the definitions are pretty crap. You instead want a rule of thumb, so that when you look at a molecule, you can be like, ionic. What was your definition? Example. Another definition. Like in general, not necessarily ionic.
Non-metals, two non-metals.
Two nonmetals is a phenomenally useless definition because both polar covalent and covalent are two nonmetals.
Okay,
So I can't differentiate between those two.
Covalent same.
Everything else is kind of a cop-out. I was kind of expecting somebody was going to do that to me.
So let's go the same or carbon hydrogen.
Yeah.
Okay? And you're right on everything else. I'm not giving you too much of a hard time for that. So your non-polar covalent are same to same or carbon to hydrogen. Okay? I dropped the non-polar because I'm lazy. Polar covalent is now everything else that doesn't fit in either the ionic or the covalent. That allows me quick and easy definitions or rules of thumb to look at a structure and say, that's the bond. The reason why I want to know that's the bond is that implies some difference in electronegativity. That difference in electronegativity tells me that the sodium and chlorine here are
An ionic bond.
rhymes with,
Positive and negative.
or a big boat. It's true. I said rhymes with, though. And it doesn't rhyme with yacht, so don't try and rhyme it with yacht. Charge. It tells us sodium and chlorine are positive and negative. Right? Because I've put that in that category, I know that to be true. I also know that in the everything else category, say if I looked at C bonded to O, that is going to start to approximate an ionic bond, which means the carbon is
Positive.
it's formally positive.
No, it is delta positive.
It
and
is
delta negative.
partially positive. Our partial symbol is that symbol for change, a lowercase delta. What happens with our covalent?
There is no or is negligible.
There is no charge. Why does this help me with our intermolecular forces? If there is no charge, you are in the perfect sharing relationship, bar none. Are you going to look for another partner? Why not? You are already happy in that relationship. If I have the perfect sharing relationship, is that molecule full of carbon and hydrogen bonds going to interact outside of it?
No.
No, which means what happens to the intermolecular force? The intermolecular force would be the one with other molecules.
It's going to be very, very weak.
It should be very, very weak. So weak that we would probably say it is 0. Until somebody comes along and says, you're wrong, it's not 0. It's small, but it's not 0. And because they did that, what do they get to do? Put their name on it. That's where we get van der Waals forces, okay? Or London dispersion. I don't know the origin of London dispersion. The best name that I've heard for this is induced dipole, induced dipole. That is also the worst name because it is a mouthful to say. Okay? But they're all meaning the same thing, meaning I'm taking a compound or a molecule that does not want to interact with the outside world, and I'm saying, how do you interact with the outside world? I don't. Stop making me. London dispersion force. Okay? Directly ties to it. What was that? Something else? What happens if I take, say, the ionic compound, and I have it interact with the outside world? It should interact very strongly. Why? It has those charges. It's trying to neutralize that charge. So I want to come up with a name that represents that really strong force. Well, where did that strong force come from?
Electrons.
From an ionic bond. So I will very intelligently name the force ionic. That was a pretty horrible name because now we get ionic bonds and ionic forces confused, which is why some people have switched ionic forces to becoming called electrostatic. It's the same connection. And if we shift to something like a polar covalent bond, carbon to oxygen, well, those aren't formally negative and formally positive, but they definitely have more charge than nonpolar covalent, which means they're going to have kind of an intermediate strength force. Okay? And I want to name that force. What do I want to name it? Okay? Di meaning 2. Pole like north and south pole. How many poles does this molecule have? Does this bond have? 1, 2. So if I take this molecule and I have it interact with another molecule just like it, I would have a dipole and I would have
A dipole.
Okay.
yeah, it's pretty legit. Yeah, there it is. Dipole-dipole force. What is the force connecting two dipoles? It's dipole-dipole. Okay, fair enough, it works. That's where our forces are coming from. They're directly tied to the bonds. So if you know the bonds, you now know the forces. Of course, we have to make it a little bit more difficult. We get hydrogen bonding, which you all know happens when?
When hydrogen comes to an oxygen, nitrogen,
Rule 2, I heard hydrogen bonded to oxygen, nitrogen, or fluorine.
Interact
okay, which is not very fun. So let's make it a little more fun. Where's the hydrogen bond in that green box?
There's none.
There is none. Your rule that hydrogen is bonding to fun, it's there.
And it has to.
Your rule sucks.
And so I paused.
Fix your rule.
All right, it has to interact with a lone pair on a hydrogen, oxygen, or nitrogen, on a bonded to another hydrogen.
It must be a dipole-dipole. You have to have a dipole-dipole. If you have a dipole-dipole, then you can ask yourself, is hydrogen present and bonded to fluorine, oxygen, or nitrogen? That's your rule set. Okay? So I would argue there isn't a fourth force. There's 3 forces, and there happens to be an extra special one called hydrogen bonding. Why do we have that extra special one?
Because it's strong.
And strong.
Ionic is strong. Why don't we just have it ionic, hydrogen bonding, and London dispersion? Why do we have hydrogen bonding as an extra special force?
Because it doesn't behave, it's a dipole-dipole that's especially strong for a dipole.
Why would I care?
It changes the way it reacts.
Dude, there's like the mountain, right? And I don't mean the physical, like the person, the mountain. He's especially strong. I don't really care about him. I don't even know his name. Why do I care about hydrogen bond?
Because it changes the way it reacts.
That was a hint. I'm not going to repeat that hint near anybody, but that's where the hint is coming from. What'd you get?
It's like the bombs and stuff.
Is that a gas? Physical property?
If you turn to the person next to you and went, what are they going to do?
Probably wipe some,
They're going to wipe?
they're going to wipe the drops off.
What are the drops?
Water.
Hydrogen bonding.
Yeah.
It's because of water. That's the only reason we have a special force in referencing hydrogen bonding, is because water makes up 70 to 80% of what we do and exist and deal with. That's why hydrogen bonding has its own special category, is because it is the most common solvent. That's why it's there. Okay? So, put this all together. We've got this kind of wheel. It needs some adaptations that I haven't done. What we start with is our strongest interaction. The nonpolar covalent interaction is the strongest interaction. As it gets progressively weaker, I decide arbitrarily that it is now a polar covalent bond. That is arbitrary. Right? Where's that arbitrary line when I shift from nonpolar covalent to polar covalent?
1.4 on.
Carbon to hydrogen.
Okay.
That's the arbitrary line. The difference in electronegativity between carbon and hydrogen, when I'm greater than that, poof, it's polar covalent. Why? Yeah, because it works. Okay, polar covalent becomes progressively weaker, 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 weaker until eventually we become ionic. Where's that line?
When electrons.
We could do metals and nonmetals, which is a nice rule of thumb that doesn't work out so well for us. It's ultimately charges is really the biggest answer. It's when we get a difference in electronegativity that is greater than some number. Okay? That number, depending on your electronegativities or the book, will change. So it's a hard line to nail down. That's why we use metal and nonmetal. We're now at an ionic bond. As that bond becomes weaker, it eventually all of a sudden goes from a bond to a force. It's still ionic, but now it's not strong enough to be called a bond, so I'll call it a force. That force gets progressively weaker until I become hydrogen bonding, until I become dipole-dipole, until I become London dispersion forces. So what we have here is a straight line continuum all the way across. Within that straight line continuum, halfway through, I said, right about there, that side, your bonds, that side, your forces. Okay? Lots of gray area. Same deal happens with each of those individual labels between it. Okay? And for those of you that don't think that is a fair assessment to make, I would ask, what colors are in the rainbow? Those of you are like, oh, I didn't think it's a fair assessment to make. I'm not going to answer that question because I don't want my worldview changed. Fair enough. Most answers become red, orange, yellow, green, blue, indigo, violet. Those are the colors in the rainbow, which is, of course, False. What colors are in the rainbow? All of them. That's why it's a rainbow. It has all of the colors. We arbitrarily decided to cut it into those blocks because I didn't want to have to memorize red, orange as a color. It also would mess up my whole memorization scheme because I'd have R, RO, O, and then orange, yellow, O, OY, Y. You wouldn't be able to do it. Okay? Same thing is happening with our bonds and forces. The reason why these things become so important is that virtually all of our physical properties come from forces. How do those individual molecules interact with each other? In the case of a melting point, if I take ice and heat it up, what does it become? Water. What did I break?
Hydrogen bonding.
I broke hydrogen bonding, which is really a force. When I boil that same water, what happens to it?
You broke hydrogen.
It evaporates, and I broke more hydrogen bonding. And in fact, I broke all hydrogen bonding. So what's left over?
Polar covalent bonds.
Polar covalent bonds. Believe it or not, and for those of you that may not have said this, it is a common question that is asked of graduate students in chemistry. Some insanely high percentage, like 30 to 40% of a graduate class, thought that when you boiled water, you broke it down into hydrogen and oxygen molecules. That's not true. Okay? It's still water, still H2O. Okay? It's a very easy concept to lose because of how interrelated these two things are. We're breaking forces, not bonds. Melting point and boiling point are based solely off of our forces. What makes it extra confusing, particularly in the case of water, what do we break?
Hydrogen.
Hydrogen bonding. So you go, oh, it's hydrogen bonding, it must be a bond. Talk to a biologist, they say it is. It's not a bond, it's a force. Stop calling it a bond. Yes, the idiot that named it was stupid and shouldn't have done it, but it's a force. Right? Solubility, vapor pressure, all of those things all contribute to forces. And the big one that we deal with, reactivity. We move after spring break, that's when we start talking about and actually during spring break, we start talking about reactions. Those reactions are dependent on forces. So you have to be able to identify those forces so that you can predict reactions. Okay? Yeah. So repercussions of forces. Okay? Melting points. Okay? It's the energy necessary for a phase change. What is resisting that phase change?
The low energy in the bond. Let's say the bond.
The low energy in a bond is resisting the phase change for melting point and boiling point.
The attraction.
The low energy in a bond is what's resisting the phase change. The low energy in the force is what's resisting the phase change. I don't care about the bond. It's the force that's dictating this. Okay? What types of species will have higher melting points or boiling points? We might expect ionic compounds. Okay? Are you referencing the ionic force or the ionic bond?
Yes. Yes.
Fair? It's a fair answer, yes. Okay? Our melting point and our boiling point will have an ionic force if it's higher. But because it has an ionic force, I also know it has an ionic bond. Delete ionic from it because those deal with metals, and we typically don't deal with metals in this class. What species is going to have a higher melting point or boiling point? You were right. I'm not saying you were wrong.
Polar covalent.
Polar covalent compounds. Why might we now shift to looking at the bond and not the force?
Because the bond dictates the force.
When we drew this guy out, right? Carbon, oxygen. I didn't draw it out this way. But we had this, right? How many of you, before we did this, have commonly written this dashed line connecting those two atoms? Fascinating. Why is that not done? What makes it different than the line?
It's a force.
It's a force and not a bond. Okay? Remember how we imply hydrogens? And guess what we also very typically imply? forces, which means when we go to evaluate these types of things, what are we looking at? The bonds, but acknowledging that those bonds will make those forces, and those forces are what dictate everything. Which, if you think about it, is kind of backwards. But that's what we do. Okay? We look at our structures, which are made up of bonds, and we see those and we say, well, that bond will generate this force. That force is strong, therefore I would have a higher melting point. We do a lot of internalization of our thought process. Okay? Review, theoretically, right? Ish? We'll accept that as an ish and just move to the next one because it's more exciting. Not really, but. Solubility. It's the ability of two things to mix homogeneously. What helps that?
Similarity of forces.
Okay. If I asked you to mix homogeneously right now, what could I do to help you mix? I'm not sure I'm following that one, but you could work with it. You're saying to get you guys to mix, put all the girls on one side of the room and guys on the other, but then aren't you unmixing? Homogeneous, I want you all evenly mixed, because right now there's a lot more people over here and not so many over here.
Decrease in this area, so we're pushing us all together.
Okay, we could change charges or change the size of the room. What if I had a cattle prod and started kind of waving that around and zapping that every so often? Do you guys think you'd mix a little faster? Why? What am I supplying?
Pressure.
Energy. What are we supplying to help things mix? Energy in what? How? We could add heat. We could add a physical motion. I could come through and physically pick you up and move you. Okay, all of these things are inappropriate, which is why I would never do them. But it's fun to imagine, right? Okay. So we're physically moving these things. We're adding heat to them to help them interact. Okay? But there's a reason we had an initial separation. We had that initial separation because they were happy in their initial states. Okay? What if they all interacted similarly? Say I take water, which has, describe water. 2 hydrogens and oxygen doesn't count. Yeah, but liquid, that works. I don't like the word polar, but I potentially like where you're going with that. If you can finish the word polar with something else. Polar covalent bonds, yes. And I took, say, ethanol, and I tried to mix them. Would they mix?
Yes. Polar covalent bonds in both of them.
Ethanol, also known as, for lack of a better word, just alcohol. You look at beer, vodka, any of those things. And water. Do they mix?
Yes.
Yeah, they actually mix really, really well. Why do they mix really, really well? And a few of you might be like, I don't know what ethanol is, dude. Why do you keep saying ethanol? That's cool. No, that's cool. Because remember, and you're like, and for those people that are laughing, like, who doesn't know alcohol? Like the structure, guys. Come on. It's just nice. If I look at the structure of ethanol, why might I say that those would readily mix?
You have the opportunity for hydrogen bonding.
Both molecules have a polar covalent bond that would lead to a dipole-dipole force. And in this case, those dipole-dipole forces also lead to hydrogen bonding. They have a similarity in forces. Okay? If they're similar, they mix well. If they're dissimilar, they don't mix. All you've got to look around the room at our population of students. Right? Look through history and see how well groups of people mix. Okay? Those similarities really help it mix. Okay? Otherwise, we have to go in and add heat and stir people, and that just in general sucks. Our rule of thumb, like forces dissolve like forces. So if we can acknowledge those similarities, we can see that those things will mix. If they have different forces, they don't mix. It's as simple as that. So looking at a compound, you should be able to predict whether it should mix with something else. So we've got water and this compound. What is this compound?
Benzene.
It is not benzene. There's 1, 2, 3, 4, 5, 6 carbons arranged in a ring. So we would call this cyclohexane. It is not an aromatic or benzene, because for it to be an aromatic or benzene, we need to have double bonds. We don't have those. Okay? So we have a cyclohexane. You started working on that nomenclature chapter yet? Probably should. Okay? Would I expect these two to mix?
No.
Okay? This has hydrogen bonding. This has, I don't see any friggin' bonds. What happened to them all? Remember those rules where we told you had simplifications? Ta-da! You have to be able to interpret and recognize that in this structure, what do we have? What are the bonds? I don't accept covalent yet because I don't even know what atoms are in there.
Non-polar covalent.
I don't expect non-polar covalent. I don't even know what atoms are present. Carbon and hydrogen. And carbon to carbon. I've now labeled the bonds that are present. By knowing the bonds that are present, I can then fit those over the layer of my definitions. Okay? And recognize that both of those fit the definition of nonpolar covalent. Because they are nonpolar covalent, I know that they generate what force? London dispersion forces. Where do London dispersion forces come from?
Covalent bond.
Induced dipole, so that's a fancy term. What is an induced dipole?
A shifting of electron density to one side or another.
Okay, so everybody got that? Everybody's okay with that? London dispersion forces are just electrons moving around. Does water have London dispersion forces?
Yes.
Does it have electrons?
Yeah.
Yes. Okay. Well, if water has London dispersion forces, aren't these similar forces? Isn't LDF the same as LDF? Shouldn't those now mix?
No.
Why not?
Hydrogen bond is stronger.
Hydrogen to oxygen, which is hydrogen bonding.
When we're thinking about our forces, we tend to really only zero in on the strongest force. It's the most dominant one, right? If you had to choose to fight someone, and let's ignore titles and roles, the mountain or me, everybody know who the mountain is?
The rock. Are you talking about?
That works. I can accept the rock too. Another geological feature that would, you'd probably also choose to not fight him instead of me. Okay, who are you going to choose? Probably me. Okay, well that sucks for me. Why are you not choosing the mountain or the rock? They're bigger. We're both people, dude. How hard could it be? There are people that have spent their lives getting bigger, stronger, faster, and deadlier. Okay, I'm spent my life getting smaller, weaker, and smarter. Which clearly isn't working well because I'm saying you should fight me. What we do is we focus on that biggest outer part aspect first. If we have to, we'll drill down deeper. But we tend to focus only at the top. Right? Because if we switch this around and said, well, cloning just became a thing. You can fight the rock or the mountain, or you can fight 30 of me. At once, like this isn't like, well, one at a time. No, 30 of me or the rock or the mountain. Who are you going to pick? You can switch your vote. They're still stronger. Why are you switching your vote? There's 30 of me. There's an amount that can factor into this. So we have kind of two competing things. The strength of our force and the amount of the force. And depending on which one's dominant, we get different results. Well, how do we know? Which would you rather fight? 30 of me or the rock? Rock. Okay. 20 of me versus the rock. Whoa.
I'll take that chance.
Damn. Okay. So we got our limit. Okay. 22 of me versus the rock. Okay. Where's that line? Because some of you are like, dude, I'm not going to fight 20 of him. Okay. I work out, sort of. Okay. That line is rather arbitrary. And ultimately, when it comes to predicting intermolecular forces and how these things, those repercussions, that line is completely arbitrary. It's experimental. Right? And we end up having to memorize kind of an arbitrary line. When it comes to melting points and boiling points, we stick pretty much solely to the strength of the force and we don't look at size effects. When we look at solubility, we get a mix of both. Right? So we picked an example already that showed this, water, which I know that says LDF, and that's kind of bothering, so I'm going to erase that. And we said hydrogen bonding, and we said ethanol dissolved, right? Cool. What do we have now? Like it looks the same. I did do a drawing. Why is that not ethanol? There's 3 points, which means I have propanol. Should that dissolve in water?
Yes. No.
Well, why not? Where was that line?
Experimentally, about 3 to 1.
1, 2, 3, 4. That fourth carbon is usually enough to outweigh hydrogen bonding. Okay? So if you look at it as 4 non-polar interactions, London dispersion forces, to 1 hydrogen bonding, okay, then they're insoluble. Very hand-wavy and arbitrary, but that's roughly where it is. Okay? So, solvent terminology. Most of what we deal with is not water, so we want to come up with ways to reference our solvents outside of water. So there's 2 big words that come out of them, and I personally hate these words, and I don't think they should ever really get used, but we're going to use them a lot this semester. We get polar versus non-polar. What are these referencing? The bonds. What kind of bonds? Don't quite accept that, because polar and non-polar bonds is a little too vague for me to say yes to that statement. Okay, our non-polar covalent bonds, that's really all I wanted to hear. Non-polar covalent bonds and our polar covalent bonds. So we could reference things as polar and non-polar by looking at their bond structure. If a structure was polar covalent bonding, we would call the molecule polar, right? If it was all non-polar covalent, we could call it non-polar as a solvent. So we're using our bonds as a classification of this. So just based off of that context alone, polar or non-polar? Polar. And just because I've been called out before, that's a carbon in the middle, and those are chlorines. I promise those are CLs. Polar or non-polar? Did I change the bonds?
No.
No. Why is it now all of a sudden non-polar? Symmetry of the molecule comes into this as well. So when we're thinking about polar and non-polar as classifications, you can use as kind of a first pass polar covalent bonds found within the solvent or non-polar covalent bonds found within the solvent. Right? Also be aware, structure can have an effect. So you should consider that. That's usually a rare consideration, but it could show up. This allows us a better generalization for our solvent terminology. So when we think of polar solvents, we're looking for solvents that have polar covalent bonds. Make sense? Right? This gets further refined. Okay? This gets refined kind of because of water. When we look at water, it has a polar covalent bond. Okay? And if I picked, say, acetone, it also has a polar covalent bond. So both of these could get classified as polar solvents. Okay? Water's polarity, though, ends up being a lot larger than acetone's. Why might it be larger?
Because you've got hydrogens connected to oxygen, the electronegativity is larger.
That's it. Electronegativity. Keep it as simple as possible. Okay, we have a larger difference in electronegativity here. which is going to cause a larger polarity. That polarity is large enough different from acetone that what do? I invent a new term. I invent a new term to reference water's excessive polarity. Okay? We now want to be able to go out and classify other compounds. So we've got a new compound down here, acetic acid. Also polar. Should it be the same polarity as water?
Yes,
Why?
because it has an accessible hydrogen.
We still have that OH down there, right? Okay. And really what we're calling attention to, because we could switch this up to now being this, isn't that still polar?
Yes.
Okay. But now we have a slight differentiation. And really the big difference that we're calling attention to is the presence of that hydrogen. Not the presence of the hydrogens out here. Well, what's the difference between the green hydrogen and the, what is that, purple boxed hydrogen? What's that? Bonded to oxygen versus bonded to carbon. Was there a special type of interaction that could potentially come from a hydrogen that was bonded to an oxygen?
Oxygen's
Yes.
got more electronegative.
That would have been called hydrogen bonding. Right? It is that hydrogen that becomes so important to us that that's really what's dictating the name of this new force. So when I had the acetic acid with that hydrogen, I'm calling attention to that functionality. Well, what is that hydrogen? Can I use a descriptor for it? I could call it a hydrogen bonding polar solvent. That's too many words. What happened to the electrons in that bond between the oxygen and the hydrogen? They're towards the oxygen, which means what does the hydrogen have?
A slightly positive charge.
Why would it have a slightly positive charge?
Because electrons are more around the oxygen.
Negative proton.
What is the only thing hydrogen would now have?
Proton.
A proton. It's protic, referencing the presence of that solitary hydrogen. Okay, that solitary hydrogen nucleus. So we have our protic solvents. The only way we get a protic solvent is if it is polar. So calling a solvent polar protic is a bit silly. Okay, that's like calling, referencing the sky is always blue sky. Yeah, the sky is blue. Why are you repeating that? You don't have to. Okay? So we could just call it protic. Aprotic, however, we could have a nuance. This carbon to hydrogen bond, is that protic? No, because the hydrogen is not naked. Why is it not naked? It's sharing electrons with that carbon, which means it's not a protic anymore, or not just a proton. There's an electron there to neutralize it. So it's not protic, so it would be aprotic. Okay? How about this carbon to oxygen double bond? Would it be protic? Why is it not protic? To be protic, what do you have to have? A negative proton. Even if this carbon was positive all by itself, would it be a proton? What would it be? A hexaproton. What's a hexaproton? What are you talking about? What's hexa? 6. Why would this be 6 protons?
Because that's the atomic number.
That's the atomic number of carbon. It can't be protic because protic by definition means 1. That would be 6. Okay? So this is not protic. It would also be aprotic. Does methane, is it going to act the same way as our acetone? CH4. Aprotic, aprotic, aprotic. So they're both aprotic. Should they both act the same way? We had 2 definitions. At the very top, we started with polar and nonpolar. When we look at the acetone, is it nonpolar? What was our definition of nonpolar? containing non-polar covalent bonds. There's acetone. What is that bond? That's polar covalent. Is acetone a non-polar solvent? No, it has a polar covalent bond, making it a polar solvent. CH4, non-polar. So yes, we can classify them both as aprotic, but we have to add that extra delineator, sure, of polar and non-polar. So when we go through and look at all of these names, I would argue we get protic, right? Then we get polar aprotic, okay, and we even go through and call this polar. Then we could get non-polar aprotic. Can I get non-polar protic? No. Okay. To be polar, you have to have that polar bond. So it can't be, that's not possible. So there's really three classifications. Okay. With the polar protic, we said the polar isn't necessary because to be protic, we have to be polar. How about non-polar aprotic?
We do need the non-polar.
We do need the non-polar. Do we need the aprotic? No. So we get three solvent classifications. Okay? So we could divide up all of our solvents into either protic, polar aprotic, or non-polar. Okay? Each of those are going to generate certain forces out of them. Non-polar came solely from non-polar covalent bonds, which means the forces from our non-polar solvents will be London dispersion forces. Our polar aprotic, dipole-dipole, and our protic, hydrogen bonding. So if we have these classifications, we now have ways that we can group and organize terms. Kind of makes sense? Okay. So we've got a bunch of solvents here. How would you classify them? Pete, I want your name, okay, and don't start ranking anything yet because you got it in two parts, okay, and we'll see the two parts on the next slide, right? There'll be two rows, or two rows. One that are all solids, one that are all liquids. I want you to rank from highest to lowest melting point. Okay, so what's the highest melting point? Number that one first, and then the lowest melting point for your solids and liquids. So there's two questions. The next one's solvent pairs. You will match each of the solids to one of the liquids that you think it's most soluble in. Okay? Alright, so you'll have 4 answers for 3. So question 1 and question 2 will just be rankings. So if we just kind of drop this out here, I believe it, whoops. I didn't mean to go back, but that works. We'd have A, bigger B, bigger C, bigger D, right? 4, bigger than 3, bigger than 2, bigger than 1. Makes sense? As answer choices. And then for 3, I would say 4B, 3A, 2A, D, C. Do I have to use everything to match? No. Make sense? Okay. There are your questions. So, it's all there. Rank for questions 1 and 2. And then for 3, match pairs that you think would be most likely to form a homogeneous mixture. No!
Goodbye.
Seriously? Don't necessarily stress, just do the best that you can. Come up with what you can. If you got questions about how to answer, you can always raise your hand. I'll come to you. Talk to the people around you. This is not expected to be a solo thing. You can discuss.
That's all I got so far. Okay. So the low, highest one would be C, right?
Yes, it'd be C.
Yeah, C, B, A, D.
Yes.
Once you've got an answer, you can try to
Now
get
it goes two, right?
Yeah.
Okay, so the most, so A is, what would make it?
So B,
A,
B
A
and
and
2.
three?
B and 2 would also be really low.
B and two, A and three?
Yes.
I agree with you.
Oh, I got it.
D.
I got
Oh, the deepest one is
I just assumed that I
yeah.
I'm not asking you to answer the question.
It's just
I know that's not chemistry there, but it's just that we just look at the words. D is the less
yeah, I think so.
Whereas, like, if you look at C, there's a lot of ones.
And then we match them.
Question two.
B's get
Oh, I see, right, so it is.
So let's identify.
I'm still waiting for it to come in.
I don't know exactly what it's called, but
So light forces go with light forces. So ignore the outside layer, basically focus on what's within it. So if you have a hydroxide group, basically hydroxide in the back. So that's why we can ignore that for now. C has an OH to match that. Those two will match.
So I didn't decide.
why not D?
Because B is a hydroxide
B
group.
is OH, H is together.
So right there, that's the poly group there. Well, A, so that has oxygen.
That is the end of time, just so you know. So if you gotta leave, you
Three.
just turn it in.
And just like
Put your name on it, and answer down. If you want to keep working, you're welcome to.
I knew one and two, and I knew A and four. I just didn't know the OH, the double bond, and O.
Yeah.
I've only done the very intro one, just how it's split. I don't even know how I need to do it. So I
Yeah.
I'll bring it. I do that.
Thursday, I'm going to think about Tuesday. Tuesday, I work all day. I work at 7 in the morning and work till 5 o'clock. That's my schedule. Tuesday, Friday, Saturday, Sunday. This lab, history of electric, and also
Okay. I rediscovered
What'd you do?
I have discovered that I am not allowed to do deadlifts.
Really? Back, say back or knees?
Back. I herniated the disc last summer, and so all of last semester was spent kind of dealing with that, and then over winter break it just seemed to kind of go away. It was awesome. So I started to lift again and lifted light, but it was not quite enough. Hoping it's just muscle to go away.
Oh, sorry, okay.
No, yeah.
I at least don't have the sciatica that I did have.
Well, I know you take one of mine, or mine already curved, so you can take one of my discs off here.
See, it's because it's hard to put it
Oh, I'm glad I was still